My name is Karthik. I will be talking about Twitter Heron. And this is kind of I'm trying to blend some kind of a data engineering and some kind of data science kind of problem that comes out of running Heron in operation. So I'll kind of spell out that problem in detail, see whether you guys can come up with some good solutions. Then you can see whether you can contribute or not. So then actually, so it's a last talk, and probably everybody will be tired. So I'll try to keep it a little bit live. I'll try to keep it live a little bit, but if you guys have any questions, just ping me, at least so that we could keep it a little bit more conversational rather than I'm monologuing all the time. Okay? Okay, so the talk outline is going to be like, first I'll give a short introduction to what Heron is, and introduce the concept of what I call is a microstream engine, and how we deal with Heron when it's running at a large scale within Twitter. And I'll zoom in on one problem called stragglers. I mean, probably everybody has heard the term stragglers in the Hadoop world, but it's not new in the big data context, but it's also occurs in the streaming world as well. Then I will also have some numbers on how the resource usage, I mean, where the time really goes, actually, when you run a streaming topology at a large scale. So I have a detailed breakdown into where the time actually goes. Then finally, I'll do some kind of conclusion about some of the problems that we face. So as you all know, like Twitter is about real time, and there are several aspects of real time within Twitter, and some of them include real time trends, where we continuously compute the trending hashtags and bubble them up so that people can consume this information. Then we also have real time conversations, where there are doing sports and everything, a lot of conversations are flowing in real time, and we wanted to bubble up those popular conversations as well. And of course, our monitoring is based on ad injection, and so if a real-time conversation is flowing, we wanted to identify what is the content of those real-time conversation, and accordingly inject those ads in real time, because as people are swiping through the Twitter's timelines, you might want to make sure that you inject the right ad that gets attention, because ultimately at the end of the day, when you click only, we do translate that into revenue for us. So finally, we have real-time search, where the incoming tweets are indexed as quickly as possible, so that when you go to search at twitter.com, you can search for those tweets right away. So these are the various aspects of real-time in Twitter, but all these tend to be accounted for billions and billions of events, and that occurs in every minute to every hour. So we need to handle all of them in real time. So that is a big challenge for us. So in order to handle all these analytics, so we have an infrastructure called Heron, which has been in production for the last 2 years. And I just give some kind of terminology. Since some of you must have heard about Storm, so it essentially borrows from all the terminologies from Storm, because it's completely backward compatible, because Twitter has invested so much on Storm and all its API that we need to carry the entire machinery without the programmers having to change anything. So a streaming job is called a topology, and it's nothing but a DAG, and all the vertices in a DAG represent the computation, and edges represent the stream of tuples flowing through those vertices. And there are two types of vertices. One is called spouts, and they are the sources of data, and the sources could be anything. Like it could be either a Kafka or a Kestrel, MySQL or Postgres, and internally within Twitter, we are in the process of replacing Kafka and Kestrel into something called Event Bus, which is based on distributed log, and that is more than 60% in production right now. So then we also have the second type of vertices called bowls, where the actual processing is happening. So in the case of a machine learning or data science problem, most of the computations will happen in those bowls. And what it does is takes the incoming tuples and munch them and emit outgoing data. And some of the examples include the real-time BA versus machine learning, where you have the filtering and aggregation, which is a very common operation. So does join as well. And also some kind of an arbitrary function, like a clustering function or a classification function. If you want to write based on whatever the job that you have, you might be able to bolt that code in and into a bolt. So a Heron topology looks like this. So you have a couple of spouts, which is in the first stage, which are tapping into multiple data streams. Then you have the second stage bowls, which are fed from the spouts. Then you have a third stage bolt, which is feeding from the second stage bowls. And one of the advantages of Heron is like you can do as many stages as you like to. Like we have seen jobs ranging from 10 stages to 15 stages, so that can keep on going. And so the next difference is like here the data is streaming. There is no notion of what you call the data is put down into a persistent storage like either SSD or a disk at every stage. Instead, the data is continuously streaming. Even if there is a process failure, the process gets restarted and data streams through again. And if the machine gets failed, the job is relocated to a different node and it continues to keep going. So to give a concrete example, in the traditional streaming world, you have this notion of a word count topology. So essentially, if you want to have a live stream of tweet and you wanted to count the number of words on that live stream of tweets, you have write a tweet spout that taps into the Twitter firehouse. And then what you do is like you take the tweet and you wanted to parse the tweet and break into words. So then once you broke the tweet into words, then you wanted to send it to a word count bowl that actually counts the words itself. So and the word count bowl will spit out how many words are occurring every second or every few seconds, depending upon how you are configured. So this, in database parlance, what we used to call is a logical plan. Yes? Yeah. Oh, okay. Okay. So it's called a logical plan if you know about database systems where if you're given SQL query, the query gets converted into some kind of an abstract query tree. And from that query tree, then you go and realize a physical plan, how it's actually executed. So that query tree is essentially nothing but a logical plan. And that is essentially what a topology is actually. Now, in physical realization, there are a lot of issues that will happen. One is the sheer amount of data that you might have to process is not possible within the realm of a single process or within the realm of a single machine itself. So in order to kind of sustain the data rate that you might be getting, so you need to allow multiple tweet spout tasks. So in other words, what we call as a parallelism. So for each of those logical plan nodes, you specify how many instances of those things have to be running at any given time. And these instances are distributed across several nodes in a big cluster. So that is what the physical realization of actually logical topology looks like. So here in this case, a tweet spout might have like a few hundred tasks. Similarly, a parse tweet bolt might have like tens of tasks. And similarly, even a word count bolt might be having another hundreds of tasks. So one of the question is, when a parse tweet bolt emits a data, where the data has to end up in the next stage or the subsequent stages. So that is where we have this notion of stream groupings. And some of the groupings include something called shuffle grouping, which is a random distribution of tuples, then which means it can go to any random downstream bowls. Similarly, you have something called fields grouping, which goes to a bolt based on the hash values of a few attributes in the Java object or the tuple. Then it's an all grouping where you replicate to all downstream bowls. And similarly, you have a global grouping where you send the entire data to one task. So with this introduction and coming back to the word count topology, how do you annotate the groupings? So between tweet spout and parse tweet, you just need a shuffle grouping because the tweet can land up at any parse tweet because it's getting just parsed. Whereas when you go from parse tweet to word count, you need a fields grouping because you want the same word to end up in the same bowl so that the count is accurate. So with this short introduction, why did Heron when we had some streaming engines? Because remember, Heron has been running in production close to 2 years after development. And so at the time, we had a lot of issues with Storm, and one of the major issues was to performance predictability. So we wanted to have predictable performance every time when you launch a job, and so that it is going at a predictable throughput, predictable latency, and everything. So then increase the developer productivity, because often one of the major complaints that we get was, hey, I'm not able to find the issue in my job. So what do I do? So at any given point of the day, we are a small team, and so we are supporting the entire massive Twitter. So which means because of the ratio of the number of jobs that are running versus the number of people that we have, we need to get to a point where users can figure out those issues by themselves, operationally as well. So only we are probably what you want to move into a stage of what you call a second level support. Only when something goes really horribly wrong, then they have to come to us. So we wanted to get the system to that level of reliability as well as productivity. Then the third one is ease of manageability. So initially we used to have manage our own clusters for Storm and everything, which we don't want to because there is a multi-tenant cluster, a huge cluster, which is probably a few 100,000 nodes that are running, and we just wanted to piggyback on this. Whereas Storm, one of the issues was that there's no notion of a resource distribution. If I'm running a topology with some X amount of resources and Y amount of memory, it can potentially exceed that. So there's no notion of those resource controls. Whereas with the new schedulers, they have this control using Linux C groups or Docker containers or whatever might be the case. So now we exploit all of those so that we can run in a multi-tenant cluster without having to worry about or maintaining another cluster and all the overhead that goes along with it, where we wanted to add more capacity, which means you have to procure new machines. Then you have to go through this buying process, get those machines, sanitize them, and add them to the cluster, and put an entry whose account that goes to. All the capacity management, I think it's much more simplified. So some of the design decisions we have to deal with is fully API compatible with Storm, even though some of the API I would have liked to change, but it's what it is. So it's all the DAGs, topologies, spouts, and everything still works in Heron. So the point is you just have to get to a point where you compile the job with the Heron jars without even changing any single line of code. So that is our kind of goal to get Heron into production. So then, as I said, the task isolation, which means ease of debuggability and resource isolation, and you should be able to profile your job. One of the major issues is, hey, where my performance is going. So I have no clue. I mean, unless you can go do a heap dump of it or profile that whatever that instance, whichever you think is slow, and you get the detailed analysis of it, boom, then you can fix your issues and move on. So then third one is the use of mainstream languages. How many of you know what language Storm was written in? Yes. So we had a little bit tough time there because not many tools were available in Clojure. I mean, even though it's a nice language, but more Lisp-like. But we had a lot of shortage of people who know about Clojure, and also the number of tools that to do mainstream development. So instead, we stuck with the desire to move Heron into more mainstream languages like C++, Java, and Python, which is very standard languages that everybody knows.
You mean the API or internally as well?
Internal level. There's no API in Clojure. All the APIs are in Java.
Right.
Yes, yeah, sure.
But you just rewrote it.
Yes, yeah. Yes? Yes. So I will show you. The beauty of Heron is, the name micro steaming engine. So if you want to write your own language native instances, go for it. Yes. So I don't want to restrict any from a developer point of view. You can bring your own language, do your own instances, boom, you're ready to go. So at a high level, Heron looks like yet another job for a scheduler. So you submit a topology to a scheduler, and then it runs the topologies as scheduler jobs. And except the only difference is the jobs don't run to termination. Instead, they keep on continuing until you kill it. So to give an idea about the little bit of the internal architecture of Heron, each topology has its own notion of a master, and that master is responsible for the entire topology. And that the topology consists of multiple runs on multiple containers, and each container has these several processes called one is the stream manager, which is responsible for routing data between containers running in the same machine as well as in across machines. And the metrics manager taps into all these various other processes that are in that container and gives you a very good visibility about what is going on in the topology, how much tuples has been emitted, what is the latency experienced by the tuple, all kind of metrics. I mean, the amount of metrics that we collect is mind-boggling. Probably for every topology, we'll be collecting around few hundreds of metrics. Then you can look at those metrics, figure out, hey, by the way, this is what's causing the issue. And the instances are where the actual work is done. So if you remember, in the topology that I mentioned, where you have a word tweet spout versus a parse tweet bold versus a word count bold, those instances are the ones that are running on these the instances. And these instances are nothing but processes. I mean, compared to Storm, which was a thread-based system, we moved into a process-based system, because process-based systems give isolation, give more control over heap dumping as well as profiling. So that's why we moved into more process-based system, and that worked out much better. So then when the topology master comes up, it comes up in a container called 0, and that is the first thing that the scheduler schedules for a topology. Once that comes up and it says, hey, by the way, I need to get more resources of, like say, 100 containers or 200 containers, then if you go and talk to the scheduler, and the scheduler in turn will say, okay, these are the machines you can spawn your containers of. Then the rest of the other containers get spawned. The first thing that comes up in the container is the stream manager. So the stream manager comes up, and the first order of business that it has to do is discover where the topology master is running. So topology master, when it comes up at container 0, it writes an entry into the zookeeper, or what we call loosely as a state manager. So it advertises its location, and everybody goes and looks at the location in the zookeeper to figure out where their address of the T master is, then connects to a T master. And the T master knows how many containers it has spawned off, so all the containers have to report back. So once all the containers report, then it forms what you call as a physical plan and pushes that physical plan down to those containers. Then once the physical plan comes into the stream manager, each stream manager knows, hey, by the way, I can connect to other stream managers. So you form what you call as a fully connected graph. So that's how the Heron works. And some of the sample topologies that we run is, you can see the complexities ranging from some very, very few simple topologies, which are like 4 nodes or 4 components in a graph, to all the way to 50 components in the graph itself. So we have all kind of topologies that are running up and running now. So it has been in production for close to 2 years. I mean, we can't give out the numbers, but as I can say, like 1 stage to 10 stages, it varies. And it's huge, massive stuff is all running on top of Twitter. And some of the use cases that I can give out is essentially like we do real-time ETL for extract data and transformations, and real-time business intelligence, and even teams like product safety that they use for continuously like fraud detection and all the various things. And the real-time trends, like all the Twitter real-time trends are being computed on top of it. Then we have some of the groups are doing even model enhancements, model building, everything in Heron as well. And even image processing related stuff all running on top of Heron as well too, where if they're sanitizing images, some of the stuff. And finally, real-time ops also. See, like since we are running massive clusters all over the board, then collecting data from those clusters continuously and figuring out what is the issues in the nodes in the cluster and everything. So we have those things as well. So I'm going to give a kind of a highlight on a couple of problems that kind of we encountered that might be good challenging problems that you might want to think about. So one is like we are living in what you call as a heterogeneous world. So I mean, you have unmanaged schedulers like Yawn and Mesos, and there are like a bunch of managed schedulers that has come up. One is Apache Aurora, which is run on top of Mesos, and Kubernetes, which is kind of managed. And Amazon ECS is another one that is Amazon has put out that runs within the Amazon EC2 instances. Then we have the Marathon, which also runs top of Mesos. Similarly, for state managers, you can use Zookeeper. Sometimes even you can use local file system. Sometimes you can even use Hadoop. And similarly, when you want to upload a job, you might want to use a Hadoop or even a web or even an S3 if you're running in an Amazon context, or even local file system if you're running entire topology in a local this thing. So in this world, how can we write a core that does not change, but all other components can be plug and played? So this is one thesis that I have is every problem in computer science revisits every 20 years. So like I said, okay, let's go and look back what people have done. So that's what there's a notion of microkernels. How many of you heard about microkernels? Okay, so initially the contention was that the kernels are so monolithic, it's very difficult to debug and all the various stuff. So then they said why we have to have all of them in the entire kernel as a monolithic. Instead, keep the basic whatever we need, and then the rest of them could be modularized or plug-and-play component that you can write on top of the basic components. And that's the idea of microkernels were born. So we borrowed the same idea with Heron, and we call this a micro-stream engine. So the basic thing that any streaming engine needs is like an intra IPCs, ability to communicate from one container to another containers, and in an either using some kind of a socket, shared memory, whatever might be the transport that you wanted to provide. And that runs on top of the hardware. Even hardware could be running on any kind of network like a 1 GB network or a 10 GB network or even an InfiniBand. So you can exploit all of them. And similarly, the notion of what you call the SPI, Service Provider Interface. We borrowed the term from Presto, which is another project that my team manages. And so the scheduler is an SPI, which means we write an abstract scheduler, but you can fit any scheduler underneath, whatever you like to. So similarly, you can do a state manager, SPI, and you can hook a zookeeper or a file system manager underneath it. So that way what happens is, a topology master does an IPC, stream manager does IPC, instance also does an IPC, and so does metrics manager. Each component is replaceable at any given time, whatever you like to. So that comes to the point, if you want to have a closure API, you go and replace your instance with a closure instance, there you go, then you have an API. So just it takes a little bit more work than just the prepackaged API, but you can get there. So that's what we intend to do with Python API and all the various other language APIs. And even metrics manager, where the collection of metrics happens, those are also goes to Scribe as well as Graphite. And there are other things also people can write. We expose that API, you can write as well. So the stream manager also even pluggable too. For example, in the streaming context, there are different processing semantics. People want like at least once, at most once, exactly once. So currently our stream manager supports at least once or at most once. So we are working on trying to get an exactly once. So the simple way to do is put another stream manager. All you have to do is in the APIs, hey, I want the semantics. So automatically the stream manager will be instantiated. The appropriate stream manager will be instantiated. So that the whole idea is the code does not change much. So in a heterogeneous environment. So similarly, the instance, the topology master is something that you don't touch all the time. So, but that is also replaceable if you know the protocol that is interacting with. So what are the advantages of micro-stream engine? Plug and play. So as the environment changes, the code does not change. So streaming still moves the data around. Second one is multi-language instances. Support for multi-language API is much easier and you get a native instances to run that API. If you want to Go instances, write your Go instances and Go API, you should be ready to go. So that is the kind of level of instances that we have done that. So then multiple processing semantics, as I said, efficient stream manager for each semantics, so that for at most ones, you can write really screamingly fast one, whereas for exactly ones, you can write very slow one because you want to checkpoint the state and replay the state. Of course, this is also the side benefit of doing this is ease of development, because teams can go really fast without depending on other components, and it increases productivity quite a bit. Sorry. So this is the environment that multi-environment that we run with. So one is a local scheduler. So essentially what we do is for developers, like people who are working inside Heron infrastructure and everybody, they said like, we don't want to debug everything in a distributed mode because it's very hard. Instead, so that's why we designed the schedule abstraction, and we have this notion of a local scheduler where you have a cluster kind of running inside your laptop, and you can bring an entire topology as though it is running on a distributed nodes in a single laptop. So that is essentially what we call as local scheduler. And then we also use local state manager, because I don't want to depend on another zookeeper and all the various stuff. You can instantiate everything local, and you're ready to go. Your Heron is up and running. And similarly for cluster and testing and other things, we run it on Meso/Aurora, and where it uses Zookeeper as state manager, and we also use HDFS for uploading the job and downloading to the nodes where the scheduler is actually running. Similarly, we also, for production, we run it in Aurora, purely Aurora, because Aurora has some other functionalities that Mesos does not have. And we use Packer Uploader, which is the internal uploader for jobs and everything, which can do even version management and all the various stuff. So that runs in cluster and production. So why Aurora? Because there are some resource quotas and other things that it can enforce. For example, as a team, I have a reservation for 1,000 cores, so you cannot exceed that. So, but you can get as much resources as 1,000 cores for all the jobs that are currently running. But the moment you exceed that, then you'll enforce those quotas. And of course, we have authorization because of Aurora. So that also comes for free when you do the authorization. And also it has an expressive DSL where you can describe the job in Aurora, like what you call is a Python variation of it. And it's so easy to use. And it also is highly available and scalable. There's a team behind managing the entire Aurora. And the cluster is probably 100,000 or something plus. So many nodes are running. And a lot of inbuilt metrics comes for monitoring and debugging, in addition to all the metrics that we export about a particular topology. So now this is one of the very important problems that we often encounter in practice. So the notion of stragglers. I mean, in any distributed systems, the stragglers are the norm. I mean, how many people have heard about the term stragglers at least? So in what context have you guys heard about it? Hadoop or, okay, so it's not new, but we also observed that often it occurs in streaming systems as well too. So, and the three primary reasons that occurs is because of something called a bad host. Especially in a large cluster, something is going to bound fail, and you are invariably with scheduler, there is a time gap between something happening to that node versus scheduler detecting it. And eventually, between the time you will get automatically scheduled, and suddenly the topology is going haywire. It's what's going on and other things. So it's I mean, among the stragglers, 80 to 90% of the time, that's what I keep hearing all the time. So the second problem is execution skew. For example, in in a fields grouping, when you have a hot key, like which Twitter is known for skewness in the data. And so the hot key can go to a single node and a single process, and that process cannot handle what it is. I mean, so that's what is called execution skew. And the third thing is what you call is inadequate provisioning. If you're not provision the job correctly in terms of resources, your input rate versus the processing rate is different. So if your processing rate is slower than the input rate, obviously you're going to go into some kind of a lag on the input data source because you're not able to clear the data. So one of the interesting problems about inadequate provisioning is today is we are doing manually. In the sense like, hey, by the way, let me run this job on this data source, internal data source, and see how it works. Then after that, I look at some graphs. Oh, the CPU is like 80 or 90%. I need some leeway. I have to bring it down to 40 or 30 or 50 around that, right? Then I add more CPU resources, then rerun the job again. So this is like a hit and trial and error kind of method that you keep on going until you find a solution, right? But can we do a better way than just doing a manual way? And so I think like there are some potential possibilities there, but we have not attempted it. One of them will involve some kind of simple machine learning and sampling. See, one thing like they can think about is like if you know the data rates, and if you sample the data in a certain sampling rate, like a 5%, 10%, 20%, and automatically run these jobs on this different sample rate and measure all these various parameters, and based on that, run some linear regression or whatever it is, and see whether this is probably the amount of resources that job will need. So that is, but the thing is, if this can be automated, and so that the user are relieved from having to do all of them trail and manual, because sometimes when they do trail manual, it is probably takes a day or probably even 2 days to get to an optimal resources. And with the provision that there could be a spike that is coming, so which means like whatever the optimal resources, you probably double X, 2X or 3X because you want to handle spikes, right? So that is an interesting problem from a data science perspective. We have not been able to solve it yet because, or rather, we don't have the time to solve it yet, but that's an interesting problem. So what are the approaches that we do in order to handle stragglers? So there are multiple approaches that you can think of. One is whoever is sending to a straggler, just find that that guy is going slow and just drop it. So that's one very simple method, but it has its own pros and cons. And second aspect is send a slow down to the speed of the straggler. So in other words, like, hey, by the way, I'm sending to the guy, he's slow, so I will also slow down. So then automatically the guy who's sending to me also will slow down so that it can propagate it continuously. Then the third aspect is direct stragglers and reschedule them. These are the potential possibilities. So the drop data strategy, where you drop the data, so one thing is unpredictable. Especially when you're running a large DAG, and consisting of several hundred containers running in a massive cluster, it's unpredictable. We don't even know where the data is being dropped, and even if it's dropped, what is the reason for it? And sometimes it affects accuracy. I mean, there are feedback from people. Hey, by the way, if you drop the data, then the accuracy becomes like inaccuracy becomes 3x. And especially if you are sharing this data to our potential partners, the accuracy has to be as good as it gets, right? So that's not a very good thing. So we need to be within a bound of accuracy. So, and also gives poor visibility about where it's being dropped and why it is being dropped. So slow down the sender strategy where this provides more predictability and it process data at the maximum rate as possible, probably at the rate at which the slowest is going in, and also reduces recovery times because the moment the straggler becomes back to normal, it will pick up speed because that's what happens, right? Then all this also can handle spikes because the data, when it arrives in spikes, you might have a temporary buffering and other things that you have to do so that you can absorb the spike quickly. So that slow down sender strategy is what implemented in Heron. And so in order to understand that, let's take a look at this simple linear topology with 4 stages. And when this topology gets realized in physical execution, you have these 4 containers, and each one of them has the 4 instances. And if B2 slows down, then what happens is the stream manager that is pumping data into B2 will come to know about it, and it will initiate a back pressure. Hey, by the way, I'm experiencing some back pressure because some of the one of my instances is slowing down. So in response to that, the stream managers will go directly to the spouts, because if you look at spouts are what you call the places where the data is injected into a topology. If you slow down the data injection, or probably not even take data, whatever the data that is currently in the pipeline to be processed will automatically slow down, and that will relieve the straggler slowness or whatever. That is the assumption. Now, so that is what will happen. Now, moment it finds that, hey, by the way, the B2 is fine, then again, relief back pressure messages will be sent to the stream managers, and then they will open up the spouts again, the data will start flowing. So this is, again, what we do. Now, you can go into this, if you open, close, open, close, open, close, we can go into the kind of flip-flop mode. So in order to kind of avoid that, or probably minimize that kind of effect, the stream managers have this notion of buffers. So large buffers, where you can configure something called low watermark and high watermark. And depending upon where the data is in the buffer, if it's below the low watermark, then you will relieve the back pressure. If it's above the high watermark, then you will initiate the back pressure. So then now, a good thing about the back pressure is if anything happens because of the slowness of B2, the lag will show up only on the source. So the moment your lag shows up on the source, you know that some back pressure is happening in somewhere. And we also pinpoint what instances in what container is causing the back pressure. Then you can go and look at that container and machine and find out what's wrong with that. So that's the way we identify these issues. So then, for example, in this case, so if there are some container that is going slow because one of the in process in that container, then essentially what it means is your read pointer is way behind the write pointer because the lag is continuously increasing, right? And there's a possibility that if the write pointer is way ahead, then you can get into swapping behavior because the messaging systems like Kafka and other things, the IO subsystems are not well designed that if you fall back, then if some of the other topologies are consuming out of the write pointer, then if you are getting delayed, then you can go into swapping behavior where you're trying to read from that late data, and that has to be brought from the disk to the memory, and which in turn affects all the topologies that are heading at the top of the right, very close to the right pointer. So that causes more problems actually. So that's one of the main rationale behind designing our own messaging system, and that's called event bus, and that solves this problem mainly. So that relieves back pressure sometimes. Now there are cases where the back pressure could be sustained because it could be because of some GC happened in that container, or because of that process is talking to somebody externally. Because in the microservices world, what happens is the streaming data would have to be joined with some other microservices, and that might not be coming back on time, right? So which means you're going at the pace of that guy because our data is not able to move because you're joining with that guy, right? And that could be another reason. So there are a bunch of other reasons that you can that can trigger back pressure as well. And so in practice, what we do is in most scenarios, back pressure recovers without any manual intervention. We are fine. This is the reason why we say this is because compared to Storm versus Heron, number of incidents that has gone down by 10x. You won't believe the amount of incidents that has gone down because of the highly reliable and the back pressure issues that we automatically injected into the topology itself. Then even in spite of that, there are some issues sometimes that happen, which is sustained back pressure, and that is attributed to these two reasons: irrecoverable GC cycles and the bad or faulty host. And bad or faulty host means like that machine will pretend that it is running. It is running something, definitely yes, but it's going slower, much slower than the other guys. So which means that costs down everybody to slow down. And sometimes user prefer dropping off the data. Sometimes what happens is some teams come and say, well, I don't worry about what do you call, if the data is getting delayed because of the back pressure and everything. I want to be at the top of the queue, but I don't care about accuracy at that point. So in order to do that, we do something called load shedding. Like moment we see the distance between the right pointer and the read pointer at any given time, and depending upon what the shredding strategy is, boom, you can jump to the right pointer or sample it and jump to the right pointer, whichever way it works. So like this is another big problem, detecting bad and faulty hosts. So today, our solution is pretty simple actually. So you have this huge cluster of containers that are running. So in order to detect these faulty hosts, what do? We run another Heron topology, which does gets the data from all the guys and gets these topology running, and these topology will continuously collect the data from these hundreds and thousands of machines and see whether that machine is reported data is good enough or not. Then once it figures out the machine is faulty, it goes and informs the SRE. Then the SRE in turn will take that machine out of the service. Now, even though it is running in real time, there is a huge amount of delay in terms of getting reported, then the SRE going and taking the machine out. So one of the interesting problems or challenges to solve is like when a topology is continuously running, so it has all set of processes that are running, and you have all the data like the CPU usage, memory, and all the various things for every container, every instances, and every process that are running on that container. So you have all of them. Now, is there any way, the moment those data come out, can you figure out these anomalies in execution? For example, if a container is going slow compared to the rest of the other containers, or the process on those containers which are correlated to that machine is going slow, can we identify some kind of real-time anomalies on the fly so that the topology itself can shoot down that container and ask the scheduler to schedule in a different one without any manual intervention? So that's a very interesting and challenging problem, because one of the things is we looked at some kind of applying Bayesian or machine learning algorithms. One of the thing that we want was like the team came back and told us like we need 2 weeks worth of data for each topology. But the topology is something that's always running real time, and you don't know what time the user is going to kill it or going to start it again, right? So whatever when they start, they might not get the same data. And again, you might schedule in a different set of nodes, which probably affect the model that you have built on top of it, right? So instead, you end up building the same model again. So another thing is 2 weeks is probably a long time to get the data before we can identify any problem, right? And this is again for every topology. As you saw, the shapes and sizes of the topology differ quite a bit. So which means like this has to run within the context of a single topology. And so like then they came back with a simpler solution where, hey, by the way, we can do threshold basis. For example, if GC, simple rule-based kind of thing where if GC goes up beyond a certain threshold, boom, alerted or whatever. But again, when you alert it, it might be okay for that topology, not for other topology. Because at the end of the day, like if you're going to hook up this to an alert system, like a guy who's waking up at 2 a.m., you better have a confidence at 95%. Otherwise, next time if you have a confidence of 20%, he's going to switch it off, he's going to go to sleep. So when a real problem occurs, right? So the confidence level has to be attained to that level. So, so we are tackling this problem, but we are not there yet. We are analyzing the effectiveness of the algorithms, adding more stuff to it, but we are not there yet. If anybody has good ideas, this is an awesome problem to solve. So as I said, sometimes people wanted to drop data, and so there are a couple of approaches that we looked at it. One is sampling-based approaches, where when you have a read and write pointers or wait ahead, then you can sample and go your way around. And when you sample, do you want to upscale the results? For example, I know that I'm sampling at the source, which means like results should be upscaled so that accuracy can be maintained. But it's very hard to do that because if, for example, when a spout is sampling, that is the only spout that might be sampling, but the other spouts in the topology might be okay. But so which means you cannot have a uniform sampling across all the spouts. And even if you wanted to achieve that, then there should be some kind of a coordination layer between the spouts in order to have that. That's all. Getting it correct is going to be extremely hard. And so in response to the amount of, or rather in a view of how much implementation will be involved, so we decided sampling might not be a good, and even upscaling the sample is going to be hard. You don't know what the computation is doing anyway. Are you doing an aggregation? Are you doing a median or a mode? So what do you upscale? So we don't know, right? So then another alternate approach is drop page approaches, where you simply drop the data and go to directly wherever the right pointer is. So Spouts takes a lag threshold and lag adjustment value and see how far we are from, and boom. And that seems to work in practice. People are happy. So that's what matters. So now before I go to the next section, which is morely about some performance numbers and everything, you have any other questions before I move further? I think I've been talking quite a bit. Okay, seems like crystal clear. Okay. So anyway, so one of the things that we wanted to analyze was what is the resource usage of Heron. So when you have a topology running, where the time is really going? Am I doing computation or am I doing data movement, which is causing that? So in order to analyze that, we did like a major breakdown of what where the time is going for the topology. And so this is a simple two-stage topology that we took. And the input to that spout is around 60 to 100 million tuples per minute. And they get filtered to 8 to 12 million tuples. And then and each of the tuple is blown up because the processing logic demands that the tuple is broken down into like what you call a flat map operation into 5x tuples. So which means it increases to 40 to 60 million tuples when it comes out of the spout itself. And those 40 to 60 million tuples per minute is shipped to the next set of bolt. And that aggregates that tuples that are coming in, then outputs that values every second at the rate of 25 to 42 million tuples per minute. So this is, and it's writing to a Redis. So this is the experimental settings and all the numbers that we have. In order to run this topology, so the number of cores that we request was around 120 cores, but the actual cores that we have taken is 30 to 50, even though like mostly it's 30 to 45 actually. And for Redis, we just gave like 2 to 4 core instances, and memory requested is and consumed was 200 GB, and only 180 was consumed, and memory requested for Redis servers is just 48 GB, which is the entire machine itself. Now, when we broke down where the performance is going, we saw the spout were taking 80% of the CPU cores, like around the 30 to 50 cores, 84% of the cores go into just spouts alone. And Bolt is complete noise, and Heron is around 7% of the overall overhead. So it's hardly anything from a Heron perspective. Now we were curious why spout is taking so long. So let's see, like investigate further more. Then the split is like this. 63% of the data, goes into deserializing, because we are taking data out of the Kafka and deserialize it, and that consumes 63% of the cores. That's where the bulk of the data is going. And then the filter operation, which we do at the spout level, that also like takes 6%. And some mapping and a few computations that we do is also noise, another 6%. And another interesting thing is the Kafka iterator and the Kafka fetch, which are essentially the code which we invoke at the Kafka to get the data from the Kafka, that takes from 16 plus 7%. That's approximately close to 25%. So we couldn't profile into that, but this is what we have measured at least. So this is where, like, as you can see, fetching, the notion of fetching data itself, 63% plus 16, that is like 73 plus around 79 plus 7, 85% of the data, spout cost is fetching data from another source. That itself is a major issue. So that's where we are paying the penalty in terms of CPU cores. So then if you profile bolts, which is already a noise from the overall, again it goes into 68% to writing data into Redis, and some amount of 19% goes into serialization. Again, the rest of them are all noise. Simple aggregation computations and all the various things are noise. So if you look at the overall, so fetching data in the overall, this thing is around 61%, and the user logic where you do is 21% of the whole cost, and Heron over is around close to 11% the overall, and 8% is writing data. So that is a split. So as you can see, in a 50 core, if 10% is 5 cores to run this massive topology, which is hardly anything. I mean, unless you optimize the 90% that is going in, you're not going to see the improve. I mean, Heron, I can even make it like a 2x, 3x faster, but that's not going to buy me anything, because as you can see, 90% of the cost is going in other places, right? So it's essential that we have efficient bolt, efficient spout, or to have a very efficient streaming system. So this is another one where we did like a 4-stage topology, which takes quite a big amount of data. And when compared with the Storm, we got a 3x reduction in resources. As you can see, like with the acknowledgements enabled, number of cores were used was 350 or whatever, or probably like 10x reduction number of cores. As you can see, Heron was using way lower cores than what Storm was using. With the no acknowledgement case, where this is at least once, this is at most once, and again, number of cores is drastically reduced. So we saved around 3 to 4x total reduction in number of cores when we migrated everything from Storm to Heron, which was done last year, last first quarter, and massive savings. So we got there. So, and if you want to know more, we have the Storm Twitter paper and Twitter Heron streaming paper. Then another one is coming out, and we have one more in the coming, which summarizes all the experiences that we had. I mean, I just pointed out a couple of problems. We have more problems that we encountered where we have a lot of solutions that we have put in. So those things will be on those paper as well. That's all I had. Any questions? Yes.
So I wanted to ask about fault tolerance.
Mm-hmm.
So do you like checkpoints at all in any of the faults, or do you need
So currently we don't do that. So, but we have finished the design for it, and we are looking to implement it. So one of the thing is like two major approaches that we wanted to do is source replay. I mean, if you, for everything like, oh, okay, I'll count on the source to save the data and give it to me. Then another one is you save the state in a bolt itself so that they're independently recoverable. So they have enough state of all the stuff and makes it independently recoverable, because you can call them as optimistic and pessimistic methods. So sources replay, I will keep going fast whenever something else, the source will have the data and I can always replay back. And in our experience, what we have seen, the source replay is not a very good idea, because in Storm, if you look at at most one semantics also counts on source to replay back. And we got badly burnt by it, actually. So what happens is sometimes you can go to the GCs and the acknowledgements don't return on time, and that means like the tuples will replay back. So if you go into a vicious cycle like that, essentially the throughput of the tuple, the entire this thing will come to a grinding halt. And you're just replaying tuples, but you're not moving further, right? So we have seen such cases. And so hence we are thinking more on the lines of what you call independently recoverable operators, so that whatever the data they get, they save it and checkpoint the data, and whatever they send it also is checkpointed. So that even if I come and run that same state, that the other guy will have its own state, this tuple I have seen, I'm not going to take it, right? So that way it becomes independent recoverable, and at a scale it works much better because it's autonomous, right? So that's one of the best properties. Even though it might go slow from a latency point of view, but since we have these 3 different semantics, you can choose whatever the semantics, but there are trade-offs. If you want more on the recovery and checkpointing, yes, you will suffer latency. But the upside of that is that it's independent recovery and all the various things become much easier. So yeah, so so we're working on it, but it'll eventually come. Yes.
Are there any plans to open source the Heron? Or?
We are working on it.
Okay.
So yes.
Just sort of curious, what is the biggest point of operating or developing a system that motivates you to just completely rewrite from scratch?
So I think I mean, I would strongly advise you to read that Heron paper because we outlined 19 problems on that. So, I mean, I have a detailed slides on this. I didn't include it in the talk because that was enumerating the storm problems and why Heron was designed. But in the gist of it is like isolation was not provided and the resource management and then a lot of GCs and other things because of interplay of multiple tasks in a single worker. Because Storm had a worker which in turn had what you call all the tasks running within a worker. And that had a lot of issues. Because of the multiplexing, you have to do demultiplexing. And if you look at the architecture, the amount of flow of the path that tuple takes and going down, it's very different. So now in Heron we cut down all of them completely, and each instance just have only 2 threads, nothing else. Just data input, user logic processing, out. That's it. And making the system much more simpler and taking advantage of some of the schedulers and everything, brought Heron into all the cool stuff that we wanted, or the essential stuff that we wanted.
Yeah, just kind of want to echo on that because like with multiple tasks within one worker is really the biggest component of JS flow. It's like
Yes.
because all the internal serialization format just make it really hard to keep progress flowing.
Yeah, so all these things, like in fact, like I can tell you a story where one of the teams was to their morning in a Runbook is every morning they have to come and click what you call rebalance the topology. That is a Runbook. They don't know why they have to do it, but it's a part of the Runbook. So then after we pushed Heron out, we didn't have the rebalance. I said like, why you need a rebalance and all? No, we are supposed to have it because the Runbook is there. Can you figure out the reason why it is having Runbook? So they sat down and we sat with them, and after that like 3 or 4 hours or probably the whole day we spent on it. Oh, there is a bug here. And then because Heron was doing the logs and everything correctly and all, right, we were able to pinpoint the bug. Then we fixed it. They didn't even touch the topology for the next 3 months. And after that, when they did a version upgrade, then they upgraded it. So there are so many stories within Twitter where you can see like how they were able to run Heron without having deal with a lot of issues. Some of the topologies that has been running for 9 months without even people touching it. We have been telling them, can you move to a new version because we are going to get out of the older versions because the UI and all the various stuff that we have designed uses some of the older protos, right? We constantly keep upgrading them. So, but again, because the stability has become, another thing is like the stream manager and the topology masters are written in C++, and so no worry about the GCs or anything because remember, these are all continuously running guys, right? And so that relieved, once the stream manager has been debugged and sturdy, we don't have to touch it. And the amount of acknowledgements and other things it can handle is way higher. So, which means like, in fact, like we actually give on a single container 1 core per stream manager. That's it. And we are not even saturated that. The one within a container, when you allocate a resource, you want some X amount of CPUs and Y amount of RAM, right? On that X amount of CPU, we do only 1 core for the stream manager, which is managed by?
And it's like managed by Mesos or?
Bezos or the
Like so the scheduling part about
the scheduling of the container is managed by Mesos, yes. Yeah, so within the container, we control the process what we run, right? So yes, so then those stream manager, even though we are only 1 core, we thought the throughput is limited. If you look at a Heron throughput, it's limited by the 1 core stream managers. So remember, all the instances can run really fast and pump data into this guy because all the data has to go from the stream manager, either even if you want to bounce back to the same container under another instance, or if you have to go outside the container and go to some other container, that also goes through via stream manager. So that single core is very busy, but we have not even hit that 80 or 90% of those things yet. So
the container you mentioned, sorry, like the container you mentioned, is it like you guys have to do back with some internal format for that, or it's just
we do a C group container. So, and I mean, we can make it Docker also, but we don't use Docker inside. So, but I mean, when you package it, you can package as a Docker. It's pretty straightforward. So, any other questions? Yes.
So I wanted to ask you how you handle any late data. I mean, if you do anything in that.
So late data, like I mean, if for out of order data.
Or I mean, like the server sent the data late, you know.
So, I mean, it's possible that the data comes in, and as long as it hits the Kafka queue, we will clear all of them. So we'll clear all of them. And the guys who are writing that, they know the timestamp where that's supposed to be returned, and they will go and hit that right bucket and update that bucket, whatever they have to do. Yes. So.
And joins, how do you handle joins?
So joins is actually like we have some bolts that do join, but now one tricky part is like if in the microservices, everybody does joins in a different service in a different way. So we can't make that pattern a little bit more common unless the services are abstracted in a, like for example, this is a classic in the streaming context, a table versus a stream join. So which means like, so your that table is format is known or schema is known or whatever it is, then I can write a generic join algorithm and boom, let's go, right? Because the microservices guys are constantly changing their thrift interfaces or whatever, right? What you get might be a little bit different today and tomorrow, right? So which means that the topologies, they update the stuff depending upon what attribute they want and other things, right? So in these cases, it's a bit hard to abstract. We have got what you call as a store as abstraction inside. People use that. Sometimes people don't even use that. They write their own stuff sometimes. So we just, that's why we have the flexibility. We have these 3 layers of API. One is the storm level or Heron level, which is the low level stuff. And 30 to 40% of the topologies run on that because they do some image processing. They want low level control and all the various stuff. And then we have the mid-level API called Hummingbird and all the various things, which allows you to more express in a DSL kind of format. That's where all the stores and all the various join could be happening. Then we have another thing called ZAR, which essentially allows you to write simple topologies using like what you call filter, aggregate, those kind of 3-stage topologies very quickly, right? So that we can do that as well too. So, any other questions? Yes.
Is there any concept of each state in this? Like, does storm doesn't hold state at all?
A state, store state?
Yeah.
The bold state?
Yeah.
So bold state, we currently like, we leave it to the user. If you wanted to write a state, you can write your state to the user itself. But now we are seeing repeated patterns of it. So what we are going to do is we are going to abstract that out. So the state, what it can observe, I mean, some of the states are so big. For example, some containers that I have seen are 30 gig. And writing that state 30 gig, how many disks you will need in order to clear that? If I have only one disk, then 30 gig divided by 100 megabytes per second, that is the interval I can write. If you have, then you have to stripe the disk to multiple within a single node to store that state, right? And I can't even go to HTFS. If you go to transfer 30 GB of bytes of data, how long will it take to transfer over the network on a 1 GB network, or I have to push that to 10 GB network? Without that, it's not going to work, right? So this is the problems with the state. So when you wanted to store the state. So that's why like, as we upgrade the hardware and everything, then that becomes more relevant. So, I mean, otherwise we lose the state, we build it up, and so that the temporary inaccuracies will be handled by some other batch job that runs like every few hours or so. So that's the way we have been doing it.
Yeah, so this is one of the slide of like state of the board itself. Say, for example, I'm processing message to message, so it's processing double by double. Is it saving any state for a particular key, say, for example?
Yeah, it can do it. Like, I mean, you can have your own map and do it, right?
You can have an external Redis cluster. You can say, hey, write this memory.
Yeah, so you can do that too.
Like, does it have anything externally built in?
Internally, we are not built in, but if you wanted to build in, one of the clear thing that we were thinking was probably a distributed Redis kind of thing that we can store. And I was also looking at how many of you guys have heard about a project at Stanford called RamCloud. So it is essentially like an in-memory key value store with a guaranteed persistence, because it replicates the data in memory of 3 nodes. Like then it's back. Only when the 3 nodes fail, you don't lose the data, which is similar to what Hadoop also does, right? So, but otherwise, like it kind of distributes the data, and also if the node goes down, then uses the memory of the other guys not to recover the data back. So, and then the data is propagated to disk asynchronously because it assumes that other memory is available, right? So that gives a guarantees in terms of persistence, right? On the other hand, Redis does not. Redis, like you store it and immediately returns back and is asynchronously propagated, right? So that's a very different.
What is it called?
Asynchronously propagated too.
The Stanford project.
It's called RamCloud.
RamCloud.
Yes, so it's so now we are looking into it. Like we have not made it run yet, but we'll see whether if that works very well, then The thing is like, if it is just a pure state for the operators, now another thing is like the operators can store that state in a distributed way. Then even when that operator goes down and probably that machine has gone down or whatever, it comes back. Then on the other node, you should be able to pick it up, right? That is one good thing. Another thing that for internal to the container, one thing that we are investigating is shared memory. I mean, a lot of people underestimate the power of shared memory. Since the shared memory is available, is similar to the memory itself, as long as somebody is holding a pointer to the shared memory, it's not claimed by the operating system. So the stream manager is kind of an internal component. So it can hold the shared memory for all the guys, and all the state can be returned on the shared memory. So even if the instance in an operator dies, they can come back up and pick up that shared memory. So which means the amount of failures becomes, it is immune to, the state becomes immune to failures at the individual node level. So you can do that as well too. So.
Just curious, is Heron majorly written in Scala?
Was it?
Is Heron majorly written in Scala?
No, it's actually like 50% in C++, 40% in, 40% in C++, 50% in Java, then some Python. So as I said, Stream Manager and the Topology Master are written in C++, whereas instance is written in Java, and the scheduler abstractions and all the various things are written in Java because they are all in the Java world, right? And the Heron UI and all the various tools are written in Python. So yeah. So like I think like there were some people who were asking, can you give me a C++ API? So I said, well, what for and all? So that we need a high speed, you know. So I said, okay. It's not very hard to write, as I said, because I have to write a new C++ instance. But even while we can provide the API, now C++ is binary, machine binary, right? I mean, the notion of transferring the job to from one binary, if you're compiling in a Mac and trying to run on a CentOS cluster, it will not work, right? You have to compile it on a CentOS cluster and throw it into a job, right? So that is the only difference that you'll get, but it's doable. So similarly, Python also, we are investigating how to make it work, yeah.
All right, guys. If anyone else is interested, feel free to stick around and keep the conversation going, but we are at time.
Okay.
I want to say so much to schedule, so if I can, thank you very much.
Thank you.